All right, good morning everybody. This is our 18th lecture on pattern recognition, and as I announced last time, it is really not so much pattern recognition we are going to do today, but rather fundamental stuff that is of great use in machine learning and pattern recognition. After having reminded ourselves what we talked about last time, I'll actually continue to talk about optimization. In the last lecture, we looked at the problem of optimization from a very fundamental point of view. We basically sort of defined it and discussed a mathematical framework that allows us to deal with constraint optimization problems. And we actually already solved a couple of them. We actually already solved a couple of optimization problems throughout our lecture so far. But when it comes to constraint optimization, last time we really did not actually talk so much about how to really do it in practice, how to implement solution algorithms or algorithms that would solve a constraint optimization problem. We went through one of them. But today we'll have to address this more practical problem, how to actually deal with that. Before we do this, I'll point out two very specific constraint optimization problems, and we will then talk about gradient descent algorithms, and then about a couple of specific algorithms for constraint optimization. And I will close with the Frank-Wolfe algorithm. And I try to close early today, at least with the content part of the lecture. So once we are done with that, don't run away, because later on we'll have to discuss the results of the survey you took a month ago as to the evaluation of the quality of the lecture. I'm supposed to discuss that with you. All right? Then let's go. Last time we talked about the problem domain of constraint optimization problems. And before I recap, let me once again point out that this minimization here should actually read argmin. When we look at problems like that, what we are interested in is not so much the smallest value of f over all the x, which would sort of this formulation hint at. We're looking for the smallest value of f over all possible x. No, what we are really interested in is the value of x for which this is smallest. And I should have written argmin. This is the difference between minimization and argminimization. However, in almost all of the texts you will find out there, they write it like this, and they drop the arg in front of the min. And so I was in this difficult situation what to do. Either be very precise in my notation or follow the general convention. Now either is bad for you. If I'm following the general convention, you may misread this. If I was very precise, you may have difficulties understanding 99% of all the text and literature out there. So please, for today, next time I'll actually be more precise. For today, this problem of minimizing over all the x, or finding the minimum of all the x in some space of a function f of x, is to be understood as that we are really looking for the x that minimizes that, not for the value of f for which this is minimum. Right? Now, a constraint optimization problem is such a problem. We are looking for some minimum or some maximum, but that minimum or maximum, and this I just multiply by -1 and we have the other, right? So it's okay if I'm talking about minimization only. That minimum, or the location of that minimum, must be in some set. This is the very general formalization of constraint optimization. We are given some function, and we are given a feasible set, some set, over which we minimize that function. That is, once again, the solution we are looking for has to be in a certain set, and cannot be an element in a well, yeah, very large vector space. It must be somewhere. So it is constrained. And a minimizer of a problem like that, say x star, is therefore a solution to that problem. And that solution may be local, maybe it's global, but maybe it is local. It is definitely a minimizer in the sense that this function at point x star is less or equal than the function at any other point x in a small epsilon environment about x star. Right? And in higher dimensional spaces, these epsilon environments are tiny balls of radius epsilon. This is why I'm writing b there. So in 3D, some function defined over three-dimensional vectors, the minimum is here, and that is to say it's at that point this function is smaller than anything else, the function in at any x inside a tiny ball about that point. And of course this is basically what we're dealing with. Some feasible set, we want to minimize something over that feasible set. In practice, saying x is to be a member of S is quite often a bit understated. So therefore, really typically, almost always, we find that set S to be characterized in terms of constraint equations. There are basically two kinds of constraints we can think of. Either equality constraints, that is to say, we are looking for an x that minimizes this function, and at the same time is such that for, I don't know, a total of p other functions g, those functions g evaluate to 0. And at the same time, we could say, well, there are even more functions, let's call them h, and for these functions h, this x has to evaluate to something less than 0, can also be greater than 0. Right? But again, I could multiply that by -1 and we are basically in the same setting. Constraints like these with the equal sign are called equality constraints, and these are called inequality constraints for obvious reasons. And one of the major things we learned last time was that if we are dealing with problems of that kind, an interesting approach is to consider the so-called Lagrangian or Lagrange function of that problem. And this is a function of, in general, 3 parameters. So L is a function of sort of those vectors x for which we are looking for the minimum, a vector lambda of Lagrange multipliers lambda, and a vector mu of Lagrange multipliers mu. So lambda is a vector of the dimension of the number of equality constraints. Mu is a vector of the dimension of the number of inequality constraints. And the Lagrangian basically is a linear combination over these functions we are given, the one we want to optimize, and the functions that define the constraints. That is, the Lagrangian is f of x plus sum over the I lambda I gi of x plus sum over the j mu j hj of x. And what is interesting about this Lagrangian, or the reason for why we look at this Lagrangian when we do optimization problems, constraint optimization problems I should say, is that we can rigorously prove, and I didn't do it, but we could if we would want to, that x star, that if x star was a solution to our problem, then there exist Lagrange multipliers lambda I star and mu I star such that the Karouche-Kuhn-Tucker conditions are fulfilled. And we then looked into the Karouche-Kuhn-Tucker conditions, and there are 4 of them. The first is called stationarity. The second one is called primal feasibility. then we have the so-called dual feasibility and what is called complementary slackness. Once again, if X star is a solution to our problem, might be the globally best solution or a local one, but if it is a solution to our constraint optimization problem, then all these conditions will be met. And by the same token, we know that if one of these conditions is violated, the solution cannot be the optimal one, right? And let's just accept that. We could make this very precise, and with respect to equality constraints, we actually looked closer into why this formalism works. And again, that was more or less from an intuitive point of view. I try to sort of, evoke some intuition for you such that you would believe me that this method of Lagrange multipliers actually works. Here we did not go into the details. Let's just accept that. We could make all of this very precise, and I said it last time, I say it again, our human civilization depends on the fact that we know that. Airplanes wouldn't fly if we couldn't optimize certain material properties of airplanes. Cars would not drive or wouldn't drive as efficiently if we could not optimize certain properties of engines of cars. Bridges would come down crumbling if we could not optimize certain physical characteristics of these bridges. So a lot of things that surround us in our daily life are the outcome of a certain optimization process, and humankind has fully understood the problem of optimization, and it boils down to what we see on this slide. And then we did something crazy. I said if that X star is indeed an optimal feasible point, then this function, the Lagrangian, at X star, lambda and mu, actually becomes a function of lambda and mu only. And that led to the definition of the so-called dual Lagrangian. Now that would be a function d of lambda and mu, which we understand to be the infimum over all the x of the Lagrangian of x lambda and mu. And this is basically to say, look at infimum of that function, which is say, let's find an x star. Plug it in here as over there. So basically, instead of infimum over all the x, I could have written Lagrangian of x star lambda. That is what that means. Now this is called the dual. It is concave. And if the Lagrange multipliers for the inequality constraints, if this is a all positive vector, then we know that the value of the dual will always be a lower bound for the optimal value of f. This is interesting because this allows us to approach optimization from a different point of view, from the point of view of the dual. Now, this is one of the slides. There are several today, which I will not discuss because we have to discuss the survey in the end. I just thought I show it to you and you go over it at home, right? So here is a lot of equations and here are some details. What I'm doing here is I'm considering this problem of regularized least squares. That is to say, we want to find a W. Note that I'm not writing arcmin here. It should be arcmin if I was precise, but in the literature nobody is as precise. So we are looking for the W that minimizes this expression. It's rather easy to do. The solution is actually this one. We've seen this before when we talked about Bayesian techniques for regression, in particular this maximum a posteriori solution to the problem. It's actually exactly this. Do you remember that when we talked about maximum likelihood under Gaussian noise assumption, we found that for regression, the solution was the same as the solution we got from the conventional least squares problem. And when we then talked about Bayesian regression, we found a solution that looked like this. There was this regularization term here. We could have done this right away by considering a certain least squares problem, namely this one. Right, so there you have it, another connection between things we studied. Long story short, if this is the problem, this is the solution we get. We can express this in terms of a new variable, let's call it lambda. We can then solve for lambda. We'll find that the solution for lambda, or the expression for lambda we find, is actually the solution to a different optimization problem, which happens to be the dual problem. We can solve this one for lambda and then use our knowledge about lambda to find the corresponding w, and this is what we get. And this is really a bit rough, so details are here, and I want you to study that at home, because this will come in very handy next week. All right, then last time we had this funny problem of the farmer who had bought a coil of wire and wanted to fence off a rectangular area of land given the length of the wire the farmer had. The problem was to determine what would be the optimal side length or side length of the fence. We looked into that and we found that we could express that as a constraint optimization problem. Now this was actually a maximization problem because the area had to be as large as possible, not minimization. But we said it could be understood as the problem of maximizing the product of the two side lengths, x1 and x2, under the constraint that 2 times the sum of the side length has to give the overall length of the wire. And this was something important we did not really make use of last time. The side length of the wire could not be negative. That would not be physical. There is no area of land with a negative side length. Mathematically that exists, but not in the physical world. So we had a constraint, inequality constraint, that would tell us the side lengths are not allowed to be negative. And at the same time, we also knew that neither of the sides could exceed a length of L, because that was the overall length of the wire. So there were a couple of constraints. We could write them down like that. And that was basically to say that in that problem we studied last time, we were dealing with half-space constraints, which is to say the solution we were after had to live somewhere to the left of the 0 along the to the right of the 0 along the x1 axis. So this is half the space R2, and it had to be above 0 along the y-axis, but it also had to be to the left of L along the x-axis and below L along the y-axis. This is what these 4 equations say. And with this, we dig into something new today. Now here are 4 vector equations. And actually, I've written them like this, deliberately written like this. I could have said such that x1 is greater than 0. That would have been boring, right? Because then we would not have recognized that this is actually about properties of 2-dimensional vectors. Here we can see that. Here I'm understanding, like with these constraints, I really understand the variable x as a 2-dimensional vector, which is the overall set in which our solution has to live in. Of course, we know that it has to be constrained. It must live somewhere in there. I've written the inequality constraints in form of vectors, and that is, of course, to say I could probably try to find a matrix vector equation to collect these 4 equations into one. And indeed, we can do that. I could summarize the 4 constraints on the previous slide in terms of just one constraint equation, where I would say, so we have a vector valued function h of a vector x And that is given by a matrix A times a vector x minus a vector b, and all of this has to be less or equal than the vector 0. And if you plug in this for the matrix A and you plug in this for the vector b, then convince yourself that this is indeed the same as that. So the long story short here is that if we are dealing with a constraint optimization problem where the inequality constraints are given in terms of half-space constraints, and of course they do not have to be axis parallel, right? We saw this problem last time where we had this crazy tilted half-spaces. But if we are dealing with inequality constraints that basically define half-spaces, such as here, we can collect those in a matrix vector equation. And that leads us back to something I mentioned much earlier throughout our lecture series, namely the notion of a convex polytope. Here this is a convex polytope. And last time we came across objects like this, and once again just a two-dimensional sketch, works in arbitrary dimensions, right? Don't be alarmed, but I cannot plot a 17-dimensional polytope. I can plot a two-dimensional one. Last time we came across the notion of polytopes, I said convex polytopes are the convex hull of a finite number of vertices. This is what we see here, right? And if I were precise, I would have said in the so-called V vertex representation, a convex polytope can be understood as the convex hull of a finite number of vertices. Now look at this. There are a couple of lines here, and of course each of these lines defines a half space, right? And therefore, if we were to intersect the, how many are there? 1, 2, 3, 4, 5. If we were to intersect those 5 half spaces, so all the points, say, above here, all the points above here, all the points to the right here, all the points to the left here, and all the points below here, if we were to intersect these 5 sets, we would get this polytope. So in the so-called H representation for half space, we can understand a polytope as the intersection of finitely many half spaces. And all of this leads to another thing I have to point out. Both of these objects are convex sets. The difference between these two objects is what? Can anybody tell me what makes them different in the sense of this will go on to infinity? Yeah.
There is no constraint that I can use this. This is unbounded by one.
This is unbounded, exactly. It is convex. We can see that, right? There will be no point in there that could not be expressed as a convex combination of any 2 points in there. You have a question?
Yes, if it's unbounded, I'm wondering what the convex hull of it is. Can it be determined or?
No.
No.
No. So this is why I call it a polyhedron. This is the difference between a polytope and a polyhedron. They are both convex sets. There is no argument about that. But this one is what we call a compact convex set. It is clearly bounded. And this one is somewhere it is not bounded. It goes on to infinity. And still, it is an intersection of half spaces. Right? So it is a convex set. This is a convex set in an H representation, but it has only 2 vertices, and sort of a couple of them are out at infinity. So there is a crucial difference between compact convex sets and open convex sets. But both of them can be understood as intersections of half spaces. And now that we have seen these kind of matrix vector formulations of inequality constraints, I can point out that in pattern recognition and machine learning, many, if not most, of the problems we are dealing with when we do parameter estimation from data come in the form of linear or quadratic programming problems. That is to say, a linear programming problem is a problem where we want to optimize some linear function over a vector of variables x under constraints like these, under half-space constraints. And a quadratic programming problem is a problem where we want to minimize a quadratic form in a vector of variables x under typically half-space constraints. Right? So if you have seen these kind of things before, from now on, you do not have to be afraid anymore. And this is basically to say, okay, so here is a linear function which we want to minimize, and apparently the solution is constrained in the sense that it has to be a point that lives in a certain intersection of half spaces. And here is a quadratic function of a vector we want to minimize, but the solution, the x we need to find, is constrained in the sense that it has to live in a certain intersection of half spaces. And seriously, most of the problems in pattern recognition and machine learning are of that form. Right? And next time we'll study that in more detail, but today it's a great occasion to return to the problem of principal component analysis, just to show you that this is a problem of that form. Have not seen that as a constrained quadratic optimization problem up until now, but let me just point out that indeed it is principal component analysis is a quadratic optimization problem. Now, without loss of generality, I assume that there is a collection, these dots here, of zero mean data. Each of the dots is called xi. We have n of them. And the fundamental problem we consider in principal component analysis is to find a set of basis vectors that are perpendicular, where these basis vectors would provide us with a coordinate system that is defined by the data itself. It's not the coordinate system of the embedding space, but a coordinate system defined by the data. And we briefly talked about it last week and talked about it extensively in the last semester, so watch these videos. Now, right now, for today, we are not interested in finding all of the principal components of the data, but just sort of the first one. Right? If we have the first one, we can sort of project all the data into space orthogonal to that direction and find the second one and so on. So we can do that recursively. Let's just look into the problem of finding a unit vector, that is to say a vector whose length is 1. We want to find a unit vector that defines a line, and the crucial characteristic of that unit vector is that if we project all the data along this unit vector onto this line defined by the unit vector, we end up with, well, one-dimensional coordinates along this line. And the variance of the projected data, so look at this, this is like sort of the leftmost point in the data set, the leftmost projected point here. This is the rightmost projected point here. So they are fairly spread apart, the projections along this line. If I were to choose another line and project the data onto this line, they are closer together. Right? So here we are interested in finding a projection vector u1 that defines a line such that if we project the data along this line, they are as far apart as possible, which is to say their variance is supposed to be as large as possible. Right? This is actually a sketch of the optimal solution in this case. This here is a sketch of another vector of length 1 that defines another line, and if we project all the data onto this line, the variance is by far not as large as here. This is exactly the property that, one of the properties I should say, that defines the first principal axis of a given set of data. So here we want to look for a vector u1 that has this property. Now, this is easy to formulate because we could say the variance, if the data is of zero mean, is basically the sum of the square of the projected coordinates. The projected coordinates result from having this vector u transpose, compute the inner product with all the data points we're given, and we want to maximize this over all u. And I said at the same time, the length of u is supposed to be 1. This is a constraint optimization problem. It's a constraint quadratic optimization problem, because here we actually look at the square of the projected coordinates. This is quadratic function in u, and it is constrained. Now, if we expand this expression here, inner product between vector u and vector xi, we find that we can write as u transpose times xi transpose times u, right? And then there is this sum over all the I, and note that today, for convenience, I have put a 1 over n in front of the sum. Why would I do this? Because I can now pull out the u's out of that summation. The summation does not depend on the u, right? The summation is just over the I, just over the vectors xi. But 1 over n times the sum xi transpose is what we call the covariance matrix. So therefore, the problem we are dealing with actually reads maximize over all the u transposed, matrix C times u, such that u transpose times u is 1. This is exactly of this form. Right? It's with an equality constraint, no inequality here, but it's an equality constraint. There is actually no linear component here, but it is definitely a quadratic optimization problem. Principal component analysis is a quadratic optimization problem. Now, how to solve this? We can look at the Lagrangian. This is exactly what we looked into last time, how we would set up the Lagrangian here. Note that I'm using a minus, whereas on the previous slides it was a plus. But on the previous slides I was talking about minimization problems, and now we're actually talking about maximization problems, and therefore minus. So once again, in all of these constraint optimization things, there's less or greater, less or equal, or greater or equal, or plus and minus and max and min. And this is, in the end, always the same by multiplying by -1, and then signs will flip. Right? And I'm really sloppy about this. I know I should probably be more precise, but that would take so much time to go through sort of like these mathematical essentials. So I just, I'm pointing out that there's a minus here where there was a plus before, but we are dealing with a maximization problem at this point. And you figure out the details by yourself. Now, this is the Lagrangian. We have the function over which we want to minimize. And we have just one constraint, and it's an equality constraint, and therefore I'm using the variable lambda to indicate that this is an equality constraint, Lagrange parameter of equality constraint. And I can turn this equation u transposed times u equals 1 into standard form by subtracting 1 on both sides. This is what I did there, right? Now then, first Cauchy-Kuntaka condition tells us that if we derive the Lagrangian with respect to the vector u, the result should be the 0 vector. So I do that. We can easily derive this Lagrangian with respect to u. We'd find that it is 2 times matrix C times vector u minus 2 times lambda times u. All of this is supposed to be 0. Therefore, we can divide both sides by 2. Doesn't matter if we divide 0 by 2. The 2 goes away. And then we move this onto the other side, and there you have it. Eigenvector, eigenvalue problem.
I have actually two questions.
Yeah.
First, that this thing actually that the solution that we got, it's sure that it is an eigenvector.
Yeah.
But all of the eigenvectors have the same property that they have the unit length as we are
Yeah.
saying.
Mhm.
But how would we say here that this is the eigenvector with the maximum eigenvalue?
Okay, I have not actually solved for the vector u yet, right? And I will not do that.
And then the second question, okay. The second question I have here, for example, the first condition that we have, the fourth condition that we have,
Yeah.
the first condition says that the derivative should be zero at the,
Mhm.
at the solution.
Yeah.
If we are actually doing the minimization problem,
Yeah.
and the function is not convex,
Yeah.
then the derivative would also be zero at the maximum of the.
Yes. Do you remember that last time we had these pictures of some crazy function, some crazy constraint surface, and I said that if we are looking at a point on the constraint surface that happens to be a local maximum or minimum of the function f, in the sense that we are now looking at a point on the constraint surface or in the feasible set, right? And that point is not only feasible, but it's also a local extremum. It is, at that point, the function we are interested in is larger than in the environment or is smaller than in the environment. Then I said, if that is given, the two gradients are parallel, right? And that is a fact of nature. And I did not prove it, but I appealed to your intuition and said that, and of course this holds here as well, right? So yes, we can really rest assured that if we are doing constraint optimization like that, we can always fall back to the Karush-Kuhn-Tucker conditions.
Actually, the thing is that the other condition that we have to actually make sure that all conditions true, then this makes sense. Otherwise, if the single is true in this case.
I don't, can you, what do we have to make sure that all the conditions?
All the conditions, 4 conditions should be met.
Yeah.
then
Here we only have to deal with 2 conditions because there are no inequality constraints, right? So we do not have to worry about this just does not exist in our problem right now. We are only talking about equality constraints. So therefore, these do actually not apply to the problem of principal component analysis. Right? These two, look, this is mu, and the mu is with respect to the inequality constraints. So these two conditions do not apply in any problem, right? For some they do, for some they don't. With respect to principal component analysis, there are no inequality constraints, just equality constraints, just constraints of this form. So we don't have to worry about that, right? And again, I have not solved for you. I have, we have to continue from here, say u equals something. I'm not doing that. All I'm doing here is to say that, this is what we know about principal component analysis, that the principal components are solutions to this eigenvector-eigenvalue equation. And now this eigenvector-eigenvalue equation pops out of a maximization problem. That's all I'm doing here. I'm just telling you that a problem you are all familiar with, the problem of principal component, is at its heart a constrained quadratic optimization problem. That's the whole purpose of this exercise. Right? And so therefore we are done with that. I'm not going to solve this any further. This is, of course, this is not a solution yet. But this is just to show that, hey, look, we have this crazy Lagrangian and then Karush-Kuhn-Tucker, and this leads to this eigenvector-eigenvalue problem. And I leave it at that. Principal component analysis is a constrained quadratic optimization problem. Now we have to get fancy. Once again, up until now, we have not actually studied algorithms that would solve these kind of problems. Right? We just familiarized ourselves with the properties these problems have. And last time actually I solved one of them. It involved matrix inversion and so on and so forth. So we saw it can be done. There's actually an algorithm for how to do it. But apart from that silly example, we did not really go into further details. And probably an even more important restriction up until this point is that really all of the pictures I've shown you and all of the problems we looked into were dealing with convex functions. Right? That is to say, here is a set of convex functions, I don't know, just simple squares, and here I have added these convex functions. So just from looking at this example, we can deduce, and we could prove that, we will not, that a function that is defined to be the sum over a series of constituent convex functions, or the sum of convex functions will be a convex function. You can see this in this picture. 3 convex functions here, simple parabola, simple quadratic functions, and this one here is the sum of them. On the right, we would see what would happen. We see what would happen if I were to multiply these 3 square functions. This black thing here is anything but convex. Right? And this is really just to, you know, sensitize you to the fact that out there, most of the things are, of course, not convex. Right? In reality, convex objective functions are not as widespread as you would believe from what we have discussed throughout the lecture so far. Of course, the reason why we like convex functions is because they have clear-cut global minima and just one of them, and quite often we try to turn a problem that is non-linear into a linear problem using Taylor expansions, for instance, or come up with tricks of how to turn convex problems into convex ones. For instance, this idea of the Lagrangian dual, I said it's a concave function, but you know, multiply it by -1, then it becomes convex. If we have an objective function that is, you know, not convex, the Lagrangian dual will always be concave, regardless. It doesn't matter. The Lagrangian dual will always be a concave function, which is easy to maximize. It has one maximum. That is one of the beautiful aspects of this theory of duality. Right? No, but in reality, a lot of problems are non-convex. And those are challenging from the point of optimization. Right? And again, like with respect to the duality formalism we have studied so far, up until now we have only seen examples where we had a convex problem in the first place, and we knew, okay, so the optimal solution is this one, and then we plug that back into the Lagrangian, and then we get this concave. Of course, if we do not know the algebraic form of the optimal problem, then we cannot plug it back into the Lagrangian. No, in general, really, we don't know where the minima or maxima of our functions are. And we therefore need different ways for how to find them. And a huge family of algorithms that allows us to do so are gradient descent methods. And let's look at what that could be. And here I have created an example of a two-dimensional function. So this is defined over x and y coordinates. So it's a function from R2 to R. And this is anything but convex. This is anything but convex. The function is the sum. I have 3xi, one, okay, you see where they are. One is here, one is there, one is there. I'm considering any point here and its distance to the 3 xi that I assume to be given. And we look at the squared distance between any point in this space, squared distance to these 3 points, take the logarithm of that and then sum it. And the result looks like that from a bird's eye perspective. Right? So this is again an isosurface representation of this function there. Definitely not a convex function. Right? And actually it's a really, well, ugly it is not, but nasty. It is of tremendous importance in physics and related fields though. The gradient of this is easy to compute. If we derive this with respect to the variable x, these are not variables, but these are parameters, they are fixed. I have 3 of them in this case. If we derive this with respect to x, we have a sum over these things, so basically the derivative will be a sum over these things because every term here depends on x. Then we have a logarithmic term in x, so as we first have to have 1 over the argument of the logarithm, that is the derivative. So this is the derivative of the logarithm. And then we have this squared Euclidean distance. The gradient of that is just 2 times x minus xi. So this is the gradient of this function. Now, we are dealing with the problem that we want to find a minimum of this function. And of course, this is another toy example, simple function defined over a plane, space R2. We can plot it, we can look at it, we find the minima, right? But if those vectors x would live in a 50,000 dimensional vector space, and maybe instead of just 3 of these sinks, we would have 27 or whatever. Like if this was generalized to a setting where we cannot plot it, then how would we come up with a minimum here? Of course, you could say, well, I don't see the problem because in order to sort of compute this, we need to know the xi, but think boldly in general. So we are dealing with the problem of wanting to find a minimum of this function. What could we do? It is not a convex function, so there will be in general, no closed form solution we could try to determine algebraically. What we can do in practice is we guess a solution, and I have called my initial guess x naught. And now we have a point x naught, and we can evaluate the function at this point x naught. And not only can we evaluate the function, we can also evaluate the gradient at that point, we can evaluate the Hessian at that point, and so on and so forth. Picture it like this: you are standing, you are hiking through the mountains, you're standing somewhere on a mountain range and you want to go downhill. You can do this. You look around in your vicinity and it goes up in my back, sort of further up the mountain. If I go to the right, then the height level stays the same. If I go to the left, the height level. If I go this way, I will go down. Right? And mathematically, that is to say, that point x is hiking in the mountains and wants to go down. Right? What can the point do? It could compute the gradient of x at this location, and then, well, the gradient will always point in the direction of steepest ascent. Put a minus in front of it and say minus the gradient is where it's down. And that is indeed the case. So what I have done here is I have computed the gradient, put a minus in front of it, and plotted the corresponding arrow. It looks like this. This is great because we want to find a minimum. And that is to say, we are at x naught right now. Let's take a step along the gradient, and everything should tell us that if we take a step in that direction, the value of the function at the next point, if we take this step, will be smaller than where it is right now. This is indeed the case. So we can take a step in that direction, Note that instead of writing minus nabla f of x, I will abbreviate that from now, delta subscript naught, here it's x naught, delta subscript step counter will be an abbreviation for minus nabla f, minus gradient. I'm too lazy to write minus gradient f all the time. So this here is to say we are at x naught and take a step into the direction of the gradient to produce a new point x1. Here is x1. But not only did we take a step in that direction, but we took a scaled step. This is the Greek letter eta, and like if we just would have taken a step of the length of the gradient, it would probably be like this, right? But if we scale it, say by a factor of 2, we do something like that. Okay? This eta here is called the step size. It allows us to control for how much we want to step into the direction of the negative gradient. Because the negative gradient, here we are talking about minimization, the negative gradient will always point downhill. Okay, let's do it. Let's do it a couple of times. This is how that looks like. I don't know how many steps that was. Let's count. 1 step, 2, 3, 4, 5, 6. After 6 steps with a fixed step size, we are there. So the system works. Looking at the plot, it appears as if we have reached a point in this error landscape, or in this, let's call it an error landscape, that is closer to one of the minima than the point where we started at. Are we very happy now?
No.
No. What could happen?
The solution depends on your starting point.
Yeah, yes, that's true. If we would have started here, we would have found another one. That there's nothing you can do about it. Like once we talk about backpropagation in neural network, what can you do?
The other thing could happen that if we fix the step size,
Yep.
maybe we overshoot the solution.
Let's see. Oh yeah. Right? So if we take the 7th step, we end up here. And if we take the 8th step with that current step size of eta, we end up here. This is because these things here are like black holes. It's the logarithm of something small. That goes down to infinity, minus infinity, like nothing. Right? Once you enter this sinkhole here, the gradient becomes humongously large. Whoosh! And you say, okay, I want to go in this direction, the gradient points in, and I want to take like 2 times the size of the gradient. And then you just overshoot, like back to a totally different area in that space. And here it so happens that this was a lucky accident actually. I didn't plan for that, but it jumped over here. Could have jumped somewhere, up there. Could have happened. Right? This is not in general. This just happened, and if I would have started here, that probably would not have happened. This is really just an accident that it jumped from there to the vicinity of another minimum. But that can really happen. This can happen, right? So here we see one problem with fixed step sizes is that we may actually really oscillate in the error landscape, and we have no control over that. Another problem could be if we would have started, far out there, then the gradient would be, let's go twice the size of the gradient. Let's go twice the size of the gradient. Let's go twice the size of the gradient. 20 years later, when we go twice the size of it, we finally make a step like this. Right? Because depending on the error landscape, if it is really, really flat, here it is anything but flat. This is like a black hole. It goes down, right? This is one side of the extremes we see here. Here the gradient becomes humongously large. Out there, it is infinitesimally small. Basically 0. And every step will be like this. And 20 years later, we arrive at some point where things become interesting. Right? So fixed step sizes are not a good idea. And one thing we can do is to try to come up with a step size that is adapted to the situation we're dealing with. And one way of doing that is called line searches. And this is one of the baffling things. Again, many of the people working in this area, like I have reviewers who rejected my papers because they didn't know what line search was. You will know it from now on. This idea of gradient descent with line searches is basically exactly what we did previously, where we said, okay, we guess a solution and then we enter a loop where we update our estimate of the location of the minimum or maximum using gradient steps with a fixed step size. That leads to a new point, and we repeat this process. Of course, there has to be some stopping criterion, but let's not ask for those. Well, we repeat that process. When we do line searches, we just basically have one other thing that needs to be done. We can try to determine an appropriate step size. And what I typically do is I say, okay, let's fix a set of step sizes. What I usually do is say here, what I did is I had a step size of 0.1, 0.2, 0.3, 0.4, 1.0, 1.1, all the way up to 2. So 20 possible step sizes. Right? Start out at x0, compute the gradient. It says go there. And then I say, okay, what would happen if I go 0.1 in that direction? What would happen if I go 0.2 in that direction? What would happen if I go 1.0 in that direction? What would happen if I go 2.0 in that direction? I have like 20 things I have to test, right? And this one actually told me go 2. So this the smallest value of f was found for the eta was 2.0 in this example. So I took a step 2 times the gradient. And that is like really basically what happened up until here. And here the gradients become large, and then it says just go 0.2 in that direction. Right? Because the gradient now was very, very large. And therefore this line search is, okay, so we know the gradient points there, and now we search along a line in this direction for the minimum of the function in our vicinity in that direction. This is why this is called line search. We are at some point xt, and we distort it by a certain step into the direction of the gradient. We evaluate the function, and we look for which step size into that direction this gives the smallest value. You can do that analytically if you're lucky. In this case, I said I used step sizes, 20 step sizes equally spaced between 0.1 and 2. Usually you would probably go for logarithmic scales, so 0.1, 0.2, 1.0, and then 2, 3, up until 10, and then 100, 200, and so on. This is how I do it. Like, you know, I have a set of candidates eta, and I just evaluate 10, 20, 30 values of that function with different etas. But that gives me control over the step size. This is called line searches. You have a question?
We could also do the inversely proportionate with the gradient as well. For example, if the gradient is very high, then there is a possibility that we could overshoot the minimum, so we could set the learning rate or step size to be very small.
Oh, we can do so many things. We can do so many things. I'll get back to that. We can do what it's called conjugate gradients. And this looks slightly more complicated. There is some more stuff we have to do before we enter this loop. And in particular, we have to compute a new parameter. I call it C for conjugate. So we start out at some point x0. We compute the gradient at that point, like the negative one, because in this example it's all about minimization. Compute the negative gradient at that point and collect this gradient in a new parameter C0. And then here is line search. We look for the sort of best local step size in the direction of the gradient and update from here to here. And now we enter this loop. We enter this loop after we have done one step already. Again, we would compute the gradient. And now this conjugate thing here is actually a linear combination of the current gradient and the gradient at the previous point in time. All right. And again, we do some line search before, like how far are we supposed to step into that direction. And the effect of this conjugate trick is basically that we will go in a more or less alternating manner. So we'll go in this direction, and then so this was actually up until here, right? So first step, nothing special happens. Second step is a step again into the direction of the gradient, and then in the third step is the second iteration of this loop. All of a sudden we do not step here, but sort of perpendicular to the previous gradient, and then perpendicular to the previous gradient, and then perpendicular and perpendicular, and so it's like have a more or less right angular approach towards the minimum. That does not have to be the case. It really depends on how we choose this parameter beta that pops up here when we compute the conjugate direction. There are different ways for how we could do that. This is called the Fletcher-Reeves update, and I have forgotten the name of that one. But you see, it does not have to be a right angular zigzag pattern. It can be something like that. But in the end, what will definitely happen is that this will approach the minimum faster. And in fact, and I'm really just throwing these things in front of you without discussing why. In fact, we can prove that if we were dealing with the problem of minimizing a convex function, so one where there is a clear-cut minimum, and say that would live in an m-dimensional space, we can prove that this conjugate gradient approach will at max take m steps until it has found the minimum of a convex function over an m-dimensional space. Here we see this. These are now convex functions, simple square functions. And they are defined over R2. And here the conjugate gradient took 1, 2 step, and it found the minimum exactly. Right? Again, I had to use something slightly different. I will not discuss what I did here, but rest assured that if you were dealing with the problem of minimizing a convex function and you were to use the method of conjugate gradients, it would take at max as many steps as there are dimensions in the space. Here we do like the minimization with respect to a convex function using fixed step sizes, and I've made it small because otherwise it would have overshot and overshot and overshot. So with a very small step size but fixed, we take, I don't know, 10 steps and still have not found the minimum. If we do line searches, then at the beginning very much progress, but the closer we come to the optimum, the more the progress slows down. Also very bad. Once again, conjugate gradients in these settings are guaranteed to find the minimum in a number of steps that is equal to the number of dimensions of the embedding space. Now you would ask, well, we know the solution to this problem. Why would we ever do this with gradients? Why?
One reason would be that the matrix inverse is numerically unstable. And
Oh yeah, that could happen, yes.
yeah,
What else could happen?
the matrix is very, well, that's the same. If the
Yeah,
matrix
but can be very unstable. That can also happen if the dimension is rather small. That can happen, like very ill-conditioned matrix. That could be, yeah. So, like pen and paper, this is the solution. There is no that. This is the solution. No question about that. On a computer, matrix A can be what we call ill-conditioned, so that the inverse there might actually be very, 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 very numerically unstable. Or what could also happen is that the dimension of that space is so huge that A transpose times A is the matrix of 1,000,000 times 1,000,000 entries, say, and then we have to invert a 1,000,000 square matrix, and that takes about 1,000,000 squared cubed iterations. Wait 10 years and come back. It's true. It's true, right? Pen and paper wise, we know the solution of quadratic problems. There is no question about that. This is the solution. And now go ahead and compute it on a computer with, I don't know, 50,000 dimensional data. It can be done, but you have to be very, very, very patient. And so therefore, really, like these iterative methods have their merit. And here we know that this one will have found the solution after 50,000 steps, say. Sharp, and it will have found the solution. And if we compute the gradient, there is no matrix inversion involved. Right? So basically the gradient of these kind of things, we've already seen one of them when we looked at this. Gradient of, where was it? Here. Gradient of these kind of square forms always looks like this. There's no matrix inversion. Of course, this may be a large matrix, but we do not have to invert it. Right? Lots of computation necessary anyway, but no inversion. So in practice, yes, indeed, that may make sense to tackle simple problems like that using these iterative approaches. Now, I do not have to talk about this one because you already did it. First project, third task. Using Newton's method, right? And see, from an abstract point of view, could have also have line searches here, don't do it. But here we basically say that the update can be understood as minus some step size, which we could determine using line search or whatever, times the inverse of the Hessian at that point, times the gradient, right? You actually really did that when you worked on task 1.3. That was exactly what you did there. Why does that work? You remember in the last semester when we talked about curvature of surfaces, Gaussian curvature, mean curvature, these kind of things. The Hessian is, in a certain sense, a measure of how bent the surface in our environment is. And the gradient says, I want to go there, and the curvature says, but steepest bend, not steepest slope, steepest bend is this way, and so therefore this is sort of compromise between this is the direction of steepest descent and this is the direction of most bend. And we see that Newton's method does not take this route, but in a sense takes a more direct route. It is basically proportional to the curvature at the point we are at.
It's always beneficial to do this one.
Pardon?
This is the better one than the...
Yeah. You know, 50,000 dimensional problem may not be possible. Really may not, right? Like this is, there is no best here. This is what I have to tell you. There's a lot of ideas out there, but none of them is the best. It just does not exist, right? I can definitely tell gradient descent with fixed step size is the worst. I can tell you that, right? The worst is no discussion. But the best, if you can easily compute the Hessian, which is the matrix of second derivatives, you did it in the first project. If you can do that, and if it is of a size that can easily be inverted, then by all means go for Newton. Right? However, if you are really, really far away from the area where the solution would live, then this would also take forever. So once again, can I say use this one in any situation? No, I can't. There is no clear-cut suggestion for what to use when, and you have to be aware of that. Right? And honestly, yeah, this is not a science. This is a craft. This is something that depends on experience rather than on proofs. For instance, here we see that conjugate gradients performs really well if the function is more or less quadratic. Now this is definitely not a quadratic function, but, and this is not necessarily the case here, but if in the vicinity of its minima the function is more or less quadratic, or has the characteristics of a quadratic function, of a convex function, then the conjugate gradients will behave just as they do in the case of quadratic functions, right? So that can be a very good idea, but it can also be a very stupid idea. It really, like, there is no clear-cut solution to that. Now, and here is just an example of where these things could have popped up in the context of the stuff we have studied so far. Here is a sample of one-dimensional points, which I actually sampled from a mixture of Gaussians. And then we studied maximum likelihood methods to determine the parameters of these Gaussians. A couple of weeks ago we said, let's assume, I don't know, variance and number of points per class are fixed. Let's just sort of use maximum likelihood to estimate the location of the means of these Gaussians. And we actually really studied briefly expectation maximization algorithm, so we know how we could do it if we were to have to estimate all the parameters, this one, and this one, and then times number of Gaussians we have. In this example, I am just assuming once again, as we did a couple of weeks ago, that we know the weight for the first Gaussian and we know the weight for the second Gaussian. And actually, I used these values to sample that. I also assume that we know the sigma of the first and second Gaussian. Now the problem is, let's find the means, right? And of course, this is one-dimensional data, but it has two means. So our optimization problem actually takes place in a two-dimensional space. This is the dimension that indicates the value of the one mean, say this one, and this is the direction that indicates the value of the other mean, say this one. So we want to find two means. This is basically an optimization problem over a two-dimensional space. Right? Here is how, well, the Lagrangian looks like, or the error. This is actually, no, okay. This is not the Lagrangian. I'm getting confused myself. This is the likelihood. Likelihood. The funny thing is, when I prepared those slides, I was wondering, should I use the log likelihood L, because we used that for the Lagrangian a couple of slides ago. And I said, context will tell. And then I ran into my own trap. I said, this is the Lagrangian, but no! Here, this is actually the log likelihood, right?
Log.
Pardon?
Log.
Log likelihood, yeah. Log likelihood. So, this is always one of the dangers. We have to infer the meaning of the symbols from context. This is the log likelihood. If I actually compute this for every pixel in this picture, this gives us an impression of how that function looks like. And it has two minima. One is here, and one is there. Does that make sense? Should that function have two minima?
Yes.
Yes, because?
Because the data says that there are two means, so the two will be actually.
Exactly. It's symmetric. I mean, the function is not symmetric, but I could say this here is mean 1. So it's actually like -3, which it is. Right? And this here is mean 2, which is 6. Right? This is the number I used, -3 and 6, when I created that data. But I can also say this here is mean 2, and this is mean 1. We don't know. Right? In that sense, it's symmetric in its parameters. The function itself is not symmetric. Right? This here is not symmetric. Can you see it? There is no mirror line anywhere. But with respect to the two parameters, it doesn't matter if I call the one -3 and the other 6, or the one 6 and the other -3. So this problem of, say, maximum likelihood estimation of only the two means of a very simple mixture of Gaussian already leads to a crazy non-convex problem. And if we were to do gradient descent, we can do this, guess a solution 0, 0, why not? And then follow the gradient. Could be done. Right. In higher dimensional spaces, might be a good idea. We could understand this as, instead of a two-dimensional problem, as a six-dimensional problem, and look for the other parameters as well. Now we would do gradient descent in a 6-dimensional space. I would have loved to plot this, but I just cannot. Okay, now quickly on to constraint optimization algorithms. And these are a couple of slides, once again, I will not discuss in the interest of time. But once again, our task is we are dealing with a constraint optimization problem. Want to minimize some function under some constraints. In practice, this can be very demanding and challenging because the data might be very high dimensional. The constraints may be nonlinear. Right? The half space constraints we've seen earlier, those are linear functions, very easy to deal with. And the function we are going to minimize or maximize may be not convex. So in general, this can be horribly, horribly tedious, difficult to do. And last time we saw a way where we had a matrix inversion there, and again, that can be done, but it may take a long time. So humankind has developed many, many ways of how to do this, how to approach constraint optimization problems. And I really just point them out and not discuss them in detail. One is called active set methods. That is, in general, we guess a solution. Maybe we can do this, maybe we can't, but let's hope that we can guess a feasible point. It may not be the optimal solution, but it's at least a feasible point. Then we compute a gradient and walk into the direction of the gradient until we hit a constraint surface. Once we have hit a constraint surface, we know that even though if the next gradient might point in that direction, we are not allowed to go there any further. So every next step we do will be orthogonal or sort of parallel, say, parallel to the constraint surface. We walk along gradients until we hit the next constraint surface. And then we have to walk in some other directions until we hit the next constraint surface. Whenever we hit a constraint surface, our set of active constraints grows. This is why it's called active sets. And that's that. And the next one, really, let's keep it at that. The next one is the huge family of barrier or interior point methods. Here, for the sake of the simplicity, I'll actually consider an equality constraint where we have a greater than. Right? This is just easier for me in the next step with the equations. But that would also work for negative constraints, like less or equal constraints. Don't worry. So we are considering some minimization problem, say, and the solution has to be greater than something. Instead of minimizing this function, we might minimize another function, let's call it B for barrier, where we say this is the original function f minus, we have different constraints here, a sum over all the constraints, but we actually take the log of the constraints. We have some epsilon in front of that. Why would we do this? This is easily recognized by looking at one picture. Here is actually a convex function we want to minimize. We know the minimum is here, but our solution has to be greater than, in this case, I guess this is the point 3 along this line. There's just one inequality constraint, and this is the point along, this is a one-dimensional problem, and we want to find a solution to this problem, but the solution has to be greater than 3, greater or equal than 3. This is the point where the constraint is active. Now, the orange line is the plot of the function we want to minimize. The blue line is a so-called logarithmic barrier. It's basically to say minus some small number times the log of that constraint function, and that looks like this. There is basically nothing going on here, and then very, very close to the constraint, whoosh, it shoots up to infinity. Now, if we compute the barrier function, it looks like this. And now we guess a point somewhere over here, follow the gradients, and eventually we reach this point. Done. The drawback is that this method, well, it's very, very simple, but it cannot find the perfect solution because it can never actually reach the point 3. The optimal solution is x is 3 for this problem here, but this barrier will actually shoot up ever so slightly before 3. Right? But if we use barrier functions like these, and look at this, basically L-shaped, nothing can happen here. Like the gradient here is always 0, we follow the gradient of this until we hit this point over there. Done. Very easy to do. Yeah, and then, oh shit, time. Projected gradients. Here, I basically consider problems like this: minimize some function x in some set, and what we do here is we compute the gradient, some step size, and this crazy notation, square brackets with a plus, indicates, okay, so we take a gradient step, and then we have to project it back into the feasible set, and we use the projected point to update our estimate. This is by all means better explained in terms of an example. And the example we will be looking into is the problem of minimizing the distance between a point Q and the convex hull of a set of points x. And let's, for the sake of simplicity, assume that we knew the vertices of this convex set. Right? Difficult to get them in general, but here we know them. We are interested in the point x star that is an element in this convex set x, an element of the hull of x. This is the convex hull of the set of points x. We want to find the point x star in this set, in the convex hull, that is closest to some query point Q. Right? So this is our minimization problem, and it's constrained like so. The solution has to be in the convex hull. I note that as a point in the convex hull, any point in this set can be expressed as a convex combination over the vertices. So we know that the solution we are after has to be a convex combination over the vertices. Can write it down like this: any point x inside the convex hull is a linear combination of the data points we are given with some weights w. And we just now want to minimize over the weights, but they have to be convex coefficients. That is, they have to sum to 1, and each of them has to be greater than 0. Right? But this is to say they have to live in the simplex. Okay, let me simplify that problem for didactic purposes. Now we want to find the closest point in a very simple convex hull, because now I can plot the space the solution has to live in. Right? This is how it would more or less look like in general, and just for didactic purposes I throw away all of this, and we talk about this line segment, which is of course a convex set, and its two vertices are called x1 and x2. And there is a crucial difference between this matrix X here, where the vectors X are given in terms of columns, and those design matrices X we have talked about before in these least square settings, where we understand X to be a row matrix. I am very, very sorry, there is nothing I can do about this. Is another of these points where I had to decide, do I write X transposes here, or do I follow the general convention in the literature? There's a difference between the design matrices X we studied earlier when we looked at least squares problem, and data matrices X we look in right now when it comes to these convex combinations. They are both called X, they both in a sense consist of the same stuff, but the one is the transpose of the other, but the transpose is not indicated. You have to infer from context what we are talking about. I am sorry about this, but this is what happens out there in the literature. All right, now, with having said that, we can now look at the problem from the point of view of the space W. Right, I said we can express every point X inside this line segment as a convex combination over the two vertices. That is to say, a convex combination over two vectors. There will be two weights. And those weights have to live on this simplex in this space. This is the space of all possible weights. Right? We have one weight 1 and one weight 2, but our solution has to be somewhere along this simplex. This is a constraint problem. If we were to choose the weights freely, the best we could get was here. But we are not allowed to choose them freely. So we guess a solution which is easy, some point in the simplex, compute the gradient at that point, and it points over here. Now if we were to take a step into that direction, we would have left the feasible set. Right? That is not acceptable. Our solution must be here. The gradient tells us go there, and it's right because the gradient of the error function points in that direction. But this is not a feasible point. We are not allowed to go there. So what we do is we project it back onto the feasible set. This is what this square bracket plus says, and of course we hide a lot of mathematical complexity in square bracket plus. These projections might be very, very, very difficult to compute. In this silly examples it's very easy. But in general, square bracket plus can be something that really takes a lot of time. You know, if the feasible set is some crazy function and you have to find the closest point, you took some gradient step and then find the damn it. That can be infeasible, right? But if we could do it, we could continue like this, you know, compute the gradient, project it back, compute the gradient, project it back, eventually come close to where the solution is. But that is of course very, very tedious. Right. So therefore, this is really, let me do it anyway. So we have to go beyond our allocated time again. There are much smarter ways of doing that. And one of these things is called the Frank-Wolfe algorithm. This is Marguerite Franck. She's a French-American mathematician, and this is Philip Wolfe, an American mathematician, who have proposed an algorithm for the optimization of convex functions over compact, we now know what that means, compact convex sets. And this is exactly the setting we were dealing with. Right? When we are looking for the closest point inside the convex hull of these 5 vertices, then that is the minimization problem of minimizing a convex function, squared distance, over a compact convex set. This is a compact convex set. So problem is already familiar to us. Here is how the Frank-Wolfe algorithm does that. We guess some solution. Once we have that solution, we enter a loop. We can compute the gradient. The gradient may point outside of the feasible set. So we can now compute the inner product between the gradient and any point inside our feasible set. Of course, you know, there are infinitely many points in a convex hull of some vertices, but let's say we could compute the gradient with respect to every point in that feasible set. That is basically to say we project the gradient onto one of the points in our feasible set. And that gives us a step direction, because this is exactly this idea of projecting something onto a set. And there is a step size which can be chosen very, very simply, or again using line searches. But the key thing here is we compute the gradient and right away project it onto the feasible set, using inner products between points in the feasible set and the gradient we've computed. Then we compute some step size, either like this or using line searches, and then we take a step into the direction of the projected gradient. The crucial observation here is that this is a linear function, and it's a linear function over a convex set. And the maximum or minimum of any linear function over a convex set will be attained at a vertex. Everybody draw the real number line, mark 2 points, then draw some linear function over that, and look for the minimum or the maximum over the interval between the 2 points. It will be at either of the points. And that holds in higher dimensions. So if we know the vertices, we don't have to test this against all possible points, but just against the vertices. For one of them, this will be largest or smallest, depending on what we want to do, and we just go in that direction. And this is how that looks like. Here, I have solved this problem actually with respect to the x-coordinates themselves. And here, actually, I have computed the gradient at this point. Look at this. If this is a convex set and we know either the vertices or a collection of points, a feasible point inside the convex set is just the mean. You can always find a feasible point. No problem there. I have computed the gradient. And in this example, I then have projected the gradient, or computed the inner product between the gradient and each of these points. Can be done with like 100 points here, but who cares? That's, easy. I have determined for which point that was largest. Happened to be this one in this case. Makes sense because the maximum of a linear function over a convex set is attained at a vertex. So the first step was actually really go from here to here. And then it began searching along this line, somewhat overshot, and then went back here where there's the optimal solution, found it in 4 steps. And if I really know the vertices, I get the same behavior at a lower cost. So in data analysis, we're given a couple of points. This will always be a finite number of points. Can be a very large number of points, but it will always be finite. Can definitely test sort of the gradient against all of them. It may be very tedious. If we knew the vertices of that set, then not as much effort, right? But the behavior is the same, because the maximum will always be attained at a vertex. And we can do the same, of course, with respect to the W parameters. Now, here I actually understood the problem really in terms of the X parameters, but I can reparameterize it again and look at the behavior of the Frank-Wolfe algorithm on the simplex, right? And now it never leaves the feasible set, but it steps from here to here to here to here, found the solution. Compare that against the projected gradient method. Yeah. And for the simplex, we of course know the vertices. These are just the unit vectors, right? And if we compute the inner product of a unit vector with the gradient, what do we get? The component of the gradient in that dimension. So we don't even have to compute the inner product. We just look for the largest entry of the gradient. This is how you do it. And we'll see how to use it next time. The funny thing is, they proposed it in 1956, and in computer science it took off about like 60 years later. To mathematicians, we computer scientists are but monkeys with keyboards. It is true. It is. I myself discovered it about at that time when that paper came out. I said, oh, this is interesting. I should probably look into it in more detail, and then put it away for 3 or 4 more years. And just about 2 years ago, I have discovered like what a beautiful idea that is for so many problems in machine learning. And look at this we are just monkeys with keyboards. It has really funny properties. It's sublinear, can be sped up. But what we know is that after t steps of that algorithm, we are of the order of 1 over t away from the optimum. So if you run it 10 times, then you are a 10th at the optimum. If you run it 100 times, you are 100 at the optimum. So you can actually, how much precision do I need? So and so much, then I do, I don't know, so and so many iterations. This is really, this thing is a beast. Today, we have learned about, this is important, different ways of how to do gradient descent. And ever so briefly looked into algorithms for constraint optimization, that is active set, interior point or boundary methods, and projected gradients. And we then, ever so briefly, but I hope that was not too brief, looked into this Frank-Wolfe algorithm for the optimization of convex functions over compact convex sets. Right. Let me point this out and go back to the polyhedron thingy. In situations like this, Frank-Wolfe is of no use to us, right? Because we are missing vertices. In situations like this, and there can be a lot, but if the set is compact, convex and compact, Frank-Wolfe is great. Here, where the set is convex but not compact, there's nothing we can do. There can always be a solution further out that's even better, right? A brutal trick would be to truncate that at some point. Just, somewhere out here, introduce another half space. Say my solution could never be larger than 1 trillion. Well, it can't, but that's hacking. But here it works, there, not really. Great, that is all I have for today. Do you have any questions? All right. Then, thank you very much. Don't run away. See you next week.